Okay, so let's try to imagine how a laser could work, right? So how does a laser work? So let's start with the simplest system we could think of, a two-level system, some initial state, ket I, and an excited state, ket K, right? And there's some initial population, Ni, in that ground state. The total population in the system, total population would just be Ni plus Nk. And the population difference, delta n, would be Ni minus Nk, right? Now initially, if it's, especially if we're talking about the visible, that energy difference is really large. There isn't going to be a lot of excited state population at all if the energy difference is big, because Boltzmann tells us that you're not going to get a lot of excited state population if you have a big energy difference between the two. So how can we get population into this state up here, right? How can we drive population into the excited state? Well, Einstein told us there are three radiative processes that we want to take a look at, right? One of those is that if we come in with a resonant photon, right? Come in with a photon that's resonant with the transition, it can be absorbed. Okay? And that will drive some population into the upper state. Then there are two ways that that light can come back down. It can come back down, right, through spontaneous emission. Right? So there's going to be some rate at which population comes back down from that upper state, and that rate is proportional to, it's equal to minus, right, because it's coming back down, Nk times the Einstein A coefficient for this transition. All right? But there's a second way for light to come back down, right? And that's stimulated emission. Stimulated emission, if we have resonant power, right, applied to this system, resonant photons, they can also stimulate emission coming back down. And then we will also have a change in population due to stimulated emission, which is equal to minus Nk, always depends on how many molecules are up there, times the Einstein B coefficient, and the resonant power density at the transition frequency. Okay, so it looks like to make a laser, what we'd like to do is apply a lot of power density and get a lot of molecules up there and have a nice big B coefficient, right? Because that's going to give us the most stimulated emission. But what we're worried about is the net rate of stimulated emission, because when we apply power density, we'll also get more absorption, right? Things are going to go up as well as come down. So now we have to look at the rate, the net rate of stimulated emission, right? Because we drive population down and we drive population up. Actually, the net rate depends on the population difference. Right? And if we're going to look at the net rate of stimulated emission, it's going to be minus delta n times the B coefficient times the resonant power density that we apply to the transition. All right. For this to be a positive number, right, we're going to have to get a population inversion, right? We're going to have more population in the upper state than the lower state. That's called a population inversion. It's not what the Boltzmann distribution wants. We need to get more population in the upper state than the lower state. how can we do that? Well, let's take a look at the rate of change of the population as we're driving things up there, right? Let's take a look at D times delta n, the population difference, right? Which would just be dni dt minus dnk dt, right? We're going to be driving population up, which depends on the Einstein B coefficient, on the applied power density, and the population difference. And we're also going to have population that's being driven down, right, minus, or driven up by absorption, excuse me, right? That depends on the Einstein A coefficient. Now initially, this term is close to zero because there's nothing in the upper state, right? So initially, it'd be great, it's going up, but eventually we're going to drive this system into steady state, right? At steady state, remember our kinetics, steady state d delta n dt is equal to 0, and therefore, right, we pop that into here, solve for delta n, and we want to see how it depends on the A coefficient, the Einstein A coefficient, the Einstein B coefficient, and on the resonant power density as well. And what we'll find is that delta n, the population difference, is equal to the total population divided by 2 times the ratio of the Einstein B coefficient to the Einstein A coefficient multiplied by the resonant power density plus 1. And now we see that it's a little more subtle than what we were thinking before. Just hit it with more power. No, if you hit it with more power, right, delta n approaches 0 as the resonant power density goes to infinity. Right? What happens is if you hit it really hard, you equalize the populations in both of these, right? This condition where we equalize the population, it goes 50-50, right? That's known as saturation. And at saturation, delta n is 0. If delta n is 0, then the net rate of stimulated emission is 0. We can never make a two-level system laze. In order to get it to laze, two-level system will never do it, right? So we're going to have to go to a 3-level or a 4-level system to do that. And so we'll show you a couple of examples. We'll start off with that YAG laser, a neodymium YAG laser, which is a 4-level system, and we'll show you how we can get that to laze.